in the last lecture we talked about theorems of failure. So in the last lecture I talked about theorems of failure. When we want to work out the strength of material, what we would do is we would undertake a uniaxial test, and we would stick a load at the two ends there. And the failure load that we work out we will call sigma capital Y. Okay? So this would be the yield strength of the material. So if you were using steel, that failure load for steel would be in the order of about, let's just call it approximately 400 newtons per millimeter squared. So when we talk about theorems of failure, we would like to relate everything back to the uniaxial test. So we do the uniaxial test to work out the stress-strain curve, which for steel would look something like that, and that would be your 400 newtons per millimeter squared, or your sigma capital Y. So that is a physical property that you can measure. So there were three theorems of failure that we talked about. So number one is the easiest one, which is called the Rankine. So we talked about this in the last lecture. The second one is quite a lot more accurate, and that one is called Tresca. And the most accurate one is called the maximum distortional energy. And I will call that von Mises. So let's just ignore Rankine for the time being, because Tresca and von Mises are more similar and also more accurate. As we said last time, it can be drawn in the principal stresses, sigma 1 and sigma 2. So that means if you know your state of stress, so if I take an arbitrary state of stress and I just make up some numbers like 200, 200, 100, 100, and I stick on some shear forces of 50 and 50. So if I just make up an arbitrary state of stress like that, how do I know if this state of stress is going to cause the material to fail? So that's the question. So it's all very well knowing your state of stress and being able to calculate the principal stresses, and it's all alright to be able to calculate your planes of failure and your tau maxes. But the real question is this safe? So as engineers, we're always asked, is this state of stress safe? So the only way that you can assess it is through one of these theorems of failure. So if we drew the Tresca one to start with, let's just draw these lines here for Tresca. So what it's basically saying is take your state of stress, which is what I've circled there, work out sigma 1 and sigma 2, which would be your principal stresses, and then compare that with the Tresca yield locus. So that means that if that value there is your sigma y, and that value there is also your sigma y, and that would mean that we are assuming that sigma y in tension is the same as sigma y in compression. Okay. So if your principal stress works out to be 500, then you would be here, and that is unsafe. So here I will put unsafe. So anything greater than that would be unsafe. And similarly, anything greater than there would also be unsafe. If, however, your sigma 1 works out to be less than 400, where 400 is your sigma yield, so if it's less than that, that would be safe. And similarly, in the other direction, in compression, that would also be your safe areas. And it doesn't take a genius to come up with a rule. You could say, just draw a straight line between those points and those points, and we can say that everything in sight there is going to be safe. So Tresca is quite nice. It's quite easy to understand. And it just tells you whether or not your material or your state of stress is going to be safe relative to the yield stress, which you get from your uniaxial tension test, assuming tension and compression are the same. So that's quite an important assumption. So von Mises is just a bit more accurate than Tresca, but it's a lot more complicated in terms of the mathematics. So I will draw von Mises around here, and you can see that instead of being a straight line around the locus points, it's a bit more curved. Okay? So at that point, that point, that point, that point, that point, and that point, so at these crosses, von Mises equals Tresca. Okay? So I hope you understand Tresca, and all I'm saying, all you need to take away is that von Mises, the failure criteria for von Mises is identical to Tresca at those points that are drawn with an X. But anything around it, say at that point, which I will call, I'll just put a question mark at that point. So at that point, using von Mises, you might get a better result, or you might be able to prove that your material is still safe. So at this point, Tresca would say it's unsafe at the question mark, but von Mises would say it's safe. So you can normally use Tresca, but if you wanted to squeeze a bit more out of the material in terms of proving to your client that the material is safe and it's not going to fail, you might like to use von Mises. So von Mises, going back to the camera, von Mises is based around distortional energy theorems. Okay? So going back 2 pages, we'll talk about strain energy. So let's take a bar or a rod like there. And we're going to stick a load P on it. And as a result of sticking that load P on it, it's going to elongate and stretch. So let's say that the original length of the bar was L0. Let's say that we've stuck a load P on at the end, and then let's say that it has deflected by V. So let's draw a graph of how P and V would interact. So at small loads, P and V would be proportional, as you can see up there. Then at larger loads, same as with the uniaxial test, it might go off like that. Okay, so P and V are no longer proportional outside the elastic limit. Now, the reason why I mentioned beyond the elastic limit is just to show that von Mises' theorem is valid for inelastic stresses. So you could probably see off here that sigma capital Y for yield that we've defined before from the uniaxial test appears at the point beyond which things become inelastic or plastic. Now, let's do a bit of calculus. So we're going to call that dV, or delta V. So let's think in terms of work. So what is the work done in extending this bar? The work done in extending this bar is equal to the integral as you extend it from 0 up to delta P dV. So we can work out the total work done in extending the bar, which is just really the area, which is really just the total area under the graph. Now, providing that, so that's work done. Now, providing that we are within this elastic region, which means that when we have stretched the bar, it recovers back to go. That means that when we release the load, it goes back to its original point, which it only would do if the stress is less than sigma y. We can work out the internal energy. And the internal energy, in this case, would then be equal to W, and that would be equal to the integral between 0 and delta. So, everything that you do from structures from this point on uses these equations. So, anything that we derive for equations in terms of getting deflections all comes from conservation of energy, which are defined by these two terms. Okay, so I'll see you tomorrow, and bright and early, and on Thursday as well.